So we want to calculate the pH of a buffer consisting of 0.45 molar of hydrochlorous acid, hypochlorous acid, and 0.62 molar of sodium hypochlorite after adding 0.04 molar of sodium hydroxide to 1 liter of that buffer. So let us write the buffer, like the expression of our buffer solution. So we have HClO aqueous plus H2O liquid reversible reaction, and the conjugate base sodium ClO aqueous plus H3O plus. So we have been told that we added 0.04 mole of sodium hydroxide to the buffer. So we're gonna remove water from this equation. So we're gonna write there sodium hydroxide. So we're gonna say aqueous over there, but remember you don't really have to include this sodium there because it's a spectator ion, does not take any it does not influence our reaction in any way, so we can just remove it. And when we remove it, we must put a negative sign over there to show that this is an ion. So when we remove that, this thing also is gonna change. So this one right here, now we have H2O instead of hydronium ion. So we have been told that initially we had 0.45 molar of the weak acid and 0.62 molar of its conjugate base. So we're gonna put that into our equations. So we have the initial, we have the change, and we have the equilibrium. So initially we had 0.45 and we added sodium hydroxide. So the concentration that we added, so the concentration of the hydroxide that we added is equal to the number of moles, 0.04 mole, divided by the volume, which is 1 liter. So the concentration basically is 0.04 molar. So we added 0.04 molar, and then the initial concentration of the conjugate base of the weak acid is 0.62, and we have nothing for water. And remember, when we add something here, according to Le Chatelier's principle, it's going the this thing is going to want to counteract with a change. It's going to fight to remove whatever that is being added. So we're gonna have a minus 0.04 molar in this side, and also here minus 0.04, because this must be removed and the reaction is going to shift in that direction. So here we have basically this reaction now is shifting towards the product, and we're going to have a plus 0.04, and we have nothing for water. And our equilibrium concentration now is going to be 0.5 0.45 minus 0.04, and that gives us 0.41. And right here we have 0. Now it's been removed, and then that side we have 0.62 plus 0.04, and that gives us 0.66, and still nothing for water. So now that we have our equilibrium concentrations, we can go ahead and find the pH of the buffer solution. But okay, let me write the Ka. So the Ka expression for this is, what is it, 2.9 multiplied by 10 to the power of negative 8. So we have the Ka expression here, which is 2.9 multiplied by 10 to the power of negative 8. So now that we have the equilibrium concentrations, we're gonna take those now. So now we have a new like a reaction. So the equilibrium reaction now. So we have HClO aqueous plus H2O liquid, reversible reaction. And so here we have the conjugate base, HClO aqueous plus H3O plus. So we have initial, change, and equilibrium. So now our initial is the one that we got previously. So our initial is going to be 0.41 and nothing for water, and our initial for the conjugate base is 0.66, and then we have 0 for the hydronium ion. So now we're gonna do this. So minus x there, nothing here, plus x and plus x. And for the equilibrium concentrations, now we have 0.41 minus x, nothing for water, 0.66 plus x, and then we have x over there. So now we're going to write the Ka expression and we solve for x. Remember, x is the concentration of the hydronium ion, which is what we need to find the pH of the buffer solution. So we're going to write this down, 2.9 multiplied by 10 to the power of negative 8 is equal to the concentration of the conjugate base multiplied by the concentration of hydronium ion divided by the concentration of the weak acid. So now we're going to substitute whatever that we have into this equation. So we have now 2.9 multiplied by 10 to the power of negative 8, and the concentration of our conjugate base, which is 0.66 plus x, and then multiply that by x divided by 0.41 minus x. So I'm just going to multiply both sides by the denominator, and I will get something like this. And now I'm going to take everything to the other side, and I will simplify my equation. So I have x squared plus 0.66x plus 2.9 multiplied by 10 to the power of negative 8x minus 11.9 multiplied by 10 to the power of negative 9. So then I can add the like terms and plug this into my calculator and solve for x. And then the value for x is 1.8 multiplied by 10 to the power of negative 8 molar. So that is the concentration for the hydronium ion. So now that we have the concentration for the hydronium ion, we can solve for the pH. So the pH for the buffer is going to be pH is equal to negative of log, multiply that by the concentration of the hydronium ion. So this is equal to negative log of 1.8 multiplied by 10 to the power of negative 8. So you can put that into your calculator and you should get something like a pH value of 7.74, and that is the final answer.